All right, in our next example, we're asked to determine where this function has intervals where we are concave up or concave down, and if there are any inflection points. So remember that when we're looking for concavity, we're looking to find the second derivative, which is really important here. Okay, so the first thing we want to do is we want to find the first derivative and the second derivative. So we're going to use our power rule here. Okay, so my second derivative turns out to be 4. The next thing that we want to do is we want to determine, are there any places where the second derivative would be 0 or where the second derivative would be undefined. Now this one is pretty interesting and actually turns out to be pretty easy because the second derivative is 4, not 4x. There are no variables here. So if I take the second derivative and I set it equal to 0, I get no solution, which means there are no points on the number line at all for me to put down into a box. So this is not possible, no solution, no variable there, no number to put on my number line. What about where the second derivative is undefined? Well, that's impossible too because the second derivative is 4, exactly 4, always 4. So 4 can never be equal to something undefined. It's not going to happen. So neither one of these are possible. So there's no solution here either. So what does this mean? Well, we have no separation points, so we're just looking at the entire number line, and we want to know for the entire number line, does the second derivative come back positive or does it come back negative? Well, if the second derivative is always just 4, 4 is always positive. So for the entire number line, it doesn't matter what point you choose, you plug it into the second derivative, you're going to come out with something positive. In fact, you're going to get positive 4 exactly. So it doesn't matter what test value that you pick. Let's say you pick 0, plug it into the second derivative, the answer will always be 4, which is always positive, no matter what. So what does that mean? Well, if it's positive, then that must mean that the graph is concave up. So what that tells me is that the entire graph from start to finish is concave up like a cup. All right? So we're going to put the entire number line. So therefore, we have no intervals for which the graph is concave down, and therefore there can be no inflection points because we never switch from concave up to concave down or vice versa. So this one's actually maybe a little bit weird, but actually really easy since there are no separation points. Actually makes testing this very easy. Okay, let's look at example 3. Now, for example 3, we need to be careful of something. We need to make sure we know how to take a derivative if we have a group of terms raised to a higher power. So remember that the first step here is to find the first and second derivative. So we don't want to stop at just the first derivative. We want second. So we're going to use the chain rule here. Let's go ahead and just write that down. Chain rule. So we're going to bring down the 4/3, and then we're going to subtract 1. So remember, we're basically subtracting 3 over 3. That gives me 1/3. It's a positive 1/3. And now we're going to find the second derivative. So we're going to use the chain rule again. We still have a group of terms raised to a higher power. So 1/3 times 4/3. So top times the top, bottom times the bottom. I get x minus 3. And then we're going to reduce that power again by 1, which means really subtracting 3 over 3. So we get negative 2/3. All right. So before I actually finish out here, I'm going to go ahead and write my second derivative with only positive exponents. Since there's a negative exponent, I'm going to go ahead and bring this down to the bottom of the fraction to join the 9. So I end up with 4 on top and then 9 times x minus 3 to the positive 2/3 power on the bottom. So here's my second derivative. And so my next step is to determine where does the second derivative equal 0 or where does the second derivative come back undefined. Alright, those are my separation points. So let's take the second derivative here, set it equal to 0. We're going to put that over 1 and we're going to cross multiply. Now we get 0 times anything is 0, and then 4 times 1 is 4. We have no variables here, so we end up with no solution. No separation points from there. What about where the second derivative is undefined? Well, we do have a variable in the denominator, So let's take our denominator with that variable in it and set it equal to 0. So does our denominator ever get a 0 in it? What x value would cause that to happen? Alright, so we're going to divide both sides by 9. And what I'm going to do actually, before I go on to the next part, well, 0 divided by 9 is 0. Let's go ahead and put that. What about 2/3? What does 2/3 mean? Well, that means that we're talking about the square root, sorry, the cube root. Let's go ahead and do that. The denominator, remember, represents the index of the radical, so we're talking about the cube root. And then the 2 on the top tells me that we're looking at squaring that. So if I want to get rid of all of that, then I'm going to take the square root of both sides. So I'm going to take square root of both sides, which still gives me 0. And then we're going to cube both sides, so we do exactly the opposite operations. Okay, so all of this is, we did a problem very similar to this in the first part of the course, looking for domains and where the functions were discontinuous. So we solved a problem very similar to this really early on. We get x minus 3 equals 0, which tells me x equals 3. So x equals 3 is one of our separation points. If we put a 3 back in place of x, I get 3 minus 3, which is 0. And multiply that 0 in, I end up with a denominator of 0, which causes the second derivative to be undefined. So we'll just keep that in mind. Alright, so my third step is to make my number line. Then I'm going to use 3 as my separation point. Remember, 3 came from where the second derivative, what x value would cause my second derivative to be undefined. So there's our separation point. Alright, I'm going to erase a little bit here so when we look back we don't have the subtractions. Alright. So there we go. So what are we doing? So we're going to choose a test value to the left and to the right. Test value to the left, the easiest one would be 0, and I think the easiest one to the right would be 4. Alright, so we're going to plug into the second derivative for each of these. Okay, so if the second derivative, if we plug in a 0, remember I'm plugging it in here, we get 4, which is positive. Divided by 9, and we get 0 minus 3 to the 2/3 power. Okay, so we have 4 over 9, negative 3 to the 2/3 power. Keep in mind something here. We're going to square this value. Remember that when we raise something to the 2/3 power, the top number tells me that I'm going to, if it's a 2, tells me I'm going to square. If I was to square a negative number, what do I end up getting? Well, the top number is always positive. We don't have to worry about that. Then I have a positive number for the 9, and then we multiply that times this. Now keep in mind that if we take a negative and we square it, which we are eventually going to do here, we always end up with something positive. So this turns out to be something positive, which means we're concave up for that interval. So the same thing is going to happen here with a positive 4. When we plug this test value in, we get 4 at the top, which is always positive. And we have 9 times 4 minus 3 to the 2/3 power. 4, which is positive, over 9, which is also positive. And then 4 minus 3, that's a positive 1 to the 2/3 power. So it's even more obvious here that we end up with a positive divided by a positive times another positive, which gives me something positive. So both of these end up with positive values, which tells us that we're concave up on either side. Alright. So let's look back at what we're asking. We're trying to find out where the graph is concave up, where is it concave down, and are there any inflection points. Two of these answers we can answer very quickly. We found no intervals for which the graph was concave down. Right? And if we don't have any transitions, notice we're concave up and then concave up again. If there are no transitions, then we cannot have an inflection point. Okay, so inflection point means we go from up to down or down to up. We do not switch. We go up and then we're up again, so there are no inflection points. So that makes this problem pretty nice and easy for those two. The last thing we want to know is the graph concave up? Can I represent this as just one big interval, or do I need to separate it into two? The key here is to look to see what happens if you plug a 3 into the original function. Do you get an asymptote, or do you get a hole? So let's just test it out. If we plug a 3 back into the original function, we end up with 3 minus 3, which is 0. 0 to any power is 0. So this is an actual point on the graph. It's not an asymptote. and it's not a hole. Okay, so it's part of the domain of that original function. So if 3 is included as part of the original function, it's a point on the graph, is not an asymptote, then we can actually include it within the interval, saying that it actually is concave up from negative infinity to positive infinity. So it's actually concave up for the entire graph. Okay. If you report it as 2 separate intervals, I will not count that off. That's fine. You can report it as negative infinity to 3 if you wished. And then again from 3 to infinity. I will not count out for that on the test. However, the proper way to do it here is negative infinity to positive infinity. That's the best way to write your interval. Right. So for example 4, once again, we want to determine where the graph is concave up and where it's concave down. Now this one's a little bit different in that when we look at our function, we have a variable already in the denominator. So before I go finding first and second derivatives, then I want to rewrite the original function. So I'm going to write this as 3, and I'm going to bring this x to the top of this little fraction here. So it's 3 plus 9, and then x, and right now it's a positive 1. If I bring it to the top, the exponent changes to being negative 1. So now, before I actually do that, I'm going to rewrite my original function. Now I'm going to take the first derivative. Pretty easy here in that the first derivative of 3 is 0. So we'll move on to the second term. The second term, I'm going to use my power rule. That's negative 9 times x. And then remember, we're going to reduce the power by 1, so I get negative 2. All right. Now we need the second derivative to determine concavity. So negative 2 times negative 9 is a positive 18, and then once again I'm going to reduce the power by 1, so I get negative 3. Alright, before I go on, since I'm going to use this to answer some questions, I'm going to go ahead and write it with positive exponents again, which means I'm going to bring x to the positive 3 power down to the bottom. Alright, so remember we're going to use the second derivative from here on out to do everything with the intervals. So I want to know, is there a place where the second derivative comes out 0? Is there a place where the second derivative comes back undefined? So let's set the second derivative equal to 0. We're going to put that over 1. Cross multiply. 0 times x cubed is 0. 18 times 1 is 18. No solution here, no variables, false statement, so no solution. What about where our second derivative is undefined? Well, we're going to take our denominator of that second derivative, set it equal to 0, and it's pretty obvious here that the second derivative would come back undefined if x was equal to 0. Alright, so our third step here, we're going to put 0 on our number line as our separation value. We're going to pick test points to the left and to the right, and we're going to plug them into the second derivative. So remember, everything that we did with the first derivative in the last section, now we're using the second derivative for everything to determine concavity. So let's put a negative 1 into our second derivative. This turns out to be really nice and easy calculations. 18 is positive. A negative number cubed is negative, so we end up with overall a negative value. So we're talking about concavity here, so we're talking about negative values tell us frown, so concave down like a frown. Positive 1. Plug that into our second derivative. So we get a positive value on the top. On the bottom, a positive value cubed is positive, so we end up with something positive. Positive things make us smile, so we're concave up like a cup. Alright, so we can report now our intervals. We're concave down from negative infinity to 0, so let's fill that in. Concave up from 0 to positive infinity. Okay, now the question comes down to inflection points. Do we have an inflection point? Well, your first thought might be, of course we do, because we definitely switch from concave down to concave up. There's a transition between the different types of concavity, so 0 has to be an inflection point. Well, one thing we want to be careful about is we want to make sure, is this an actual point on the graph, or is this an asymptote or a hole? If it's an actual point on the graph and we transition, then we can say yes, it's an inflection point. If that point at x equals 0 turns out to be an asymptote or a hole, then we don't actually have a point on the graph there. We have an asymptote or a hole, and that cannot be an inflection point. So let's go back to the original graph, the original function here. F of x equals 3 plus 9 over x. What happens when we plug 0 into that function in place of x? Well, 9 divided by 0, that's undefined. How can I add 3 plus undefined? Well, I can't. The whole entire thing becomes undefined, which means, since we're not allowed to get something undefined out of a function, that means that at this particular point, we have an asymptote. Okay, it doesn't cancel out. Can't cancel out that denominator of x there, so definitely an asymptote there. So therefore, since it's an asymptote, it's not an actual point on the graph, then we don't have any inflection points, because it's not a point. The keyword here being a point on the graph, not an asymptote. An asymptote is not a point. Okay, so we have no inflection points for this particular problem because x equals 0 turns out to be an asymptote. Alright, so now we're going to look at kind of a nice and easy one in a way. F of x equals x to the fourth. Nice and easy in that the first and second derivatives are very straightforward. We get 4x cubed for our first derivative. The second derivative turns out to be 12x squared. So that's pretty nice and easy. We're looking for concavity, remember, so we're finding the second derivative. And everything we do from here on uses the second derivative. So the second derivative, 0. What x values would cause that? Second derivative, undefined. Let's go ahead and rule out finding something where the second derivative is going to be undefined because we have no variables in a denominator, no negative exponents to bring down, so that's not going to be possible. So we're just going to set our second derivative equal to 0. And let's solve for x. So I divide both sides by 12, x squared equals 0. Take the square root of both sides, we get x equals 0 as our one and only separation point. Alright, so we can pick some test values, remember, to the left and to the right. Pretty easy values, -1 and +1. And remember that we're plugging them into the second derivative, really important. So the second derivative is here. And notice that the first thing that we do with our x values is we square them. So that turns out to be a +12, which tells me concave up. +1, same thing. The first thing I'm going to do when I plug it into that second derivative is I'm going to square it. So we end up with something positive, +12 again. So we're concave up again. Alright, so we're concave up from, so now can we include 0 as part of our interval? Since we're concave up to the left and to the right, can we include 0 as part of the interval? Well, it depends on if 0 is an actual point or an inflection, or an asymptote. So is it a point or an asymptote? So let's go back over here. If we plug 0 into the original function, do we have a problem? And no, we don't. If I plug 0 into the original function, I get out 0. So that means that I can include 0 as part of the interval. So we're concave up from -infinity to +infinity. There's no asymptotes. We're not concave down anywhere. And since we don't have a transition from up to down or down to up, then we have no inflection points. All right, so our last example, we're going to look at a real-world problem here. All right, so it tells us that the total sales S in thousands of dollars of this particular corporation, this corporation manufactures automobile air conditioners. So it says here that the total sales S, let's kind of redo here, total sales S in thousands of dollars is related to the amount of money X that's also in thousands of dollars. This is related to the amount of money that's spent on advertising. Okay, so X represents the money in thousands of dollars spent on advertising, and S, the output of our function, represents the total number in sales, also in thousands of dollars. We're asked to find the inflection point of the function S. All right, so in order for us to determine an inflection point is where we transition from concave up to concave down or concave down to concave up. So if I'm looking for an inflection point, that tells me that what I need to eventually get to is that second derivative. So let's find the first derivative first. We have some decimal values, but of course we can just use our calculator. So 3 times negative 0.01 turns out to be negative 0.03. Reduce our exponent by 1. 2 times 1.5, so ignore the double positives there. Just one of those is all we need. What do we get for that? Well, 2 times 1.5 is 3. And then reduce our power by 1, so I just get 3x. And of course, 200, the derivative of that is 0. All right, so this makes finding our second derivative also pretty easy. 2 times negative 0.03, I get negative 0.06. Reduce our exponent by 1, and of course this one's just 3. Alright, so we want to determine where the inflection point is. So we're going to set our second derivative equal to 0, or we want to look for where the second derivative of the function comes back undefined. Once again, we do not have a negative exponent on any of our variables, and we don't have any variables in any denominator, so cross that out. That's not possible. So let's see where our second derivative would come back equaling 0. Okay, pretty easy equation to solve. I'm going to bring 3 to the other side, so we're going to subtract that over. Then I'm going to divide both sides by negative 0.06, and I end up with a positive value. I end up with actually a positive 50. So if we think about what we're actually finding here, remember x equals 50 represents $50,000. This is the amount of money that's spent on advertising. Let's see what's happening to the left and to the right, just to prove that we do have a transition point that represents this inflection point. So let's pick test values to the left and to the right. Now, you could pick 49 to being to the left of 50, but I'm going to pick something really easy. Just anything to the left of 50. Isn't 0 to the left of 50? Yes, it is. So I'm going to use that. That's a lot simpler to calculate. If I plug a 0 into my second derivative, we get a positive 3. Really nice, really easy. Concave up to the left of 50. And then to the right, when we plug, let's choose 51. Second derivative, plug in a 51. I end up getting out something that is negative. Alright, so plug that in. Negative 0.06 times 51. And then add 3. So I end up with a negative 0.06. So that's definitely negative, which comes out telling us that we have concave down. Alright, so we have shown that there is an inflection point on the graph, and we do want to verify that it is actual point on the graph. So once again, we're going to put in an x value of 50 back into the original function, just to make sure that it's not an asymptote, that we actually get a legitimate value out when 50 goes in. Okay, so we're going to throw that into our calculator exactly as is. Pretty nice, pretty easy. I end up with 2,700. So it is an actual point on the graph, and the inflection point would be the x value and also the y value of that point. So what does this actually mean for the sales? So let's kind of scroll down here. It's kind of interesting when it comes to finding this inflection point and why you care about the inflection point. A point is reached after which any additional advertising expenditure results in increased sales, but at a slower rate of increase. So what you want to know is, are you getting the biggest bang for your buck? So you're spending all of this money on advertising. Is it worth it? Are you getting back a really good return on your investment? All right, so there's a point what we call the point of diminishing returns, and that turns out to be that inflection point. This is the point of diminishing returns. So what happens here is that your sales are increasing, but here they're accelerating at a greater speed. So here, your concave up, that means that your sales are increasing at a faster rate. So it's kind of like you're accelerating in your car, you're getting faster and faster and faster. At one point, you start to slow down. So faster increase here. And then here on this side, you start to slow down. So that means that you're not getting as much money. When you're spending all this money on advertising, you're not getting as much money back in sales anymore. This is what we call the point of diminishing return. After some point, all of a sudden your sales start to slow down.